Okay, we'll be starting with some basic concepts on multivariate analysis. So let us define what we call by a multivariate random vector. Let us denote by x a set of p random variables x1, x2, xp. So this is a random vector of random variables where these xi's are random variables defined on a probability space omega script f p. Now some basic concepts of multivariate analysis will be actually defining some simple concepts. We'll make distinction between discrete multivariate random vector and continuous multivariate random vectors. So we define first the distribution function. Distribution function of this multivariate random vector x is defined to be f x1, x2, xp at the points x1, x2, xp. This is defined as the following, that it is probability that minus infinity less than x1 less than equal to x1 and the last random variable minus infinity less xp less than equal to small xp. So this is how a distribution function of a multivariate random variable is defined. Let us now make a distinction between discrete multivariate random variable and continuous multivariate random variable. Suppose we have discrete multivariate distribution. Then this distribution function f x1, x2, xp at small x1, x2, xp points, this is defined to be summation k-fold, p-fold rather. So over all these points where we have probability that x1 equal to say I1, xp equal to ip, where these now I1 is less than equal to small x1 and ip is less than equal to this xp point. So this particular quantity for a discrete multivariate random variable is defined in this following way. Now given the joint distribution function of this set of p random variables constituting this multivariate random vector, we can define marginal probability mass functions, joint mass functions. So the probability mass function, or rather the joint probability mass function of this multivariate random vector x is defined in the following way, that it is probability that x1 equal to small x1, xp equal to small xp. So we call this particular quantity the joint probability mass function. Now given this, the joint probability mass function of this random vector x as we had defined, we can find out what is called the marginal distributions. The marginal probability mass function of say any random variable in this particular set of p random variables x1, x2, xp, say xi, is defined to be probability that xi equal to small xi. So this is given by a p minus 1 fold summation, which is except this xi random variable. So this is probability over the sum over the joint probability mass function. Okay. Like here we have probability x1 equal to x1 extending up to this probability that this we have the joint probability mass function, right? Now this is the marginal probability mass function of one random variable xi in the set of the multi-dimensional random vector, which is comprising of x1, x2, xp. Now in a similar way one can actually define the joint probability mass function of any set of variables taken from this multidimensional random vector x1, x2, xp. Say the joint probability mass function of two random variables xi and xj taken from this set of this multidimensional random vector xi, say x. The joint probability mass function of xi xj is defined to be in a similar way to what we had defined for the marginal probability mass function of one random variable. So this can be defined as probability xi equal to xi, xj equal to xj. This is sum. Now the sum is p minus 1 fold. It is over all xi's except xi and xj, and then we have this joint probability mass function of all the random variables. Right. When we have the joint probability mass function of any set of variables taken from the multidimensional random vector x comprising of those p components, one can define distributions which are referred to as conditional distributions. Say, suppose we are interested in knowing what is the conditional distribution of any set of variables taken from this p-dimensional random vector given another set of random variables. Say, let us be simple and try to look at the following, which we say that say the conditional distribution of x, say any k given xi and xj. So in order to find what is the conditional distribution of xk given xi and xj, we look at the following, that probability that xk equal to xk given that xi equal to small xi and xj, the random variable, equal to small xj. So this would be given by the following, that this is the joint probability mass function of these three random variables xi, xj and xk, this divided by the marginal probability mass function of the two random variables xi and xj. So here what we have basically, in order to find out the conditional distribution of one random variable given two random variables xi, any two random variables xi and xj, of course xi and xj are not included in this xk here, it can also be. But when we look at this, it is basically this numerator in this conditional distribution of xk given xi and xj is the joint probability mass function of xi, xj and xk, and the denominator is xi and xk's joint probability mass function. Right. Let us now move on to the case of conditional or rather the marginal distributions, the conditional distributions in case of continuous multivariate random variables. How it looks like. Continuous multivariate distribution. So we had first of all defined what is the joint distribution function of any a set of multivariate random components. So in case of a continuous multivariate distribution comprising of these p elements, this for a continuous distribution would be defined through the integral. We assume that the set of random variables form a set of absolutely continuous variables. So we will have that being defined through the following function, small f function, which we are going to define shortly. So this is defined to be the following, and then this is product of xi's I equal to 1 to p. Now the function that we have introduced here is what is called the joint probability density function of these random variables. So this quantity is what we refer to as the joint probability density function, or in short PDF, of this random vector x. Now this is given by, so this quantity is given by the following. So it's the pth partial differential, this with respect to the variables that we have, if the differentiation exists at the point x1, x2, xp, if the derivative exists at x1, x2, xp and is equal to 0 if it is otherwise, right? So for a continuous random vector x, this quantity is of interest, and what we refer to that as the joint probability density function. Now given this joint probability density function, in a way similar to what we had done for discrete random vector, we can define a marginal probability density function of a set of random variables taken from that multivariate random vector. We can define conditional distributions exactly in the same way as what we had done for a discrete distribution. Say for example, we can look at the marginal, say, joint PDF of xi and xj. So there are two variables taken from this set of p random variables. So this would be defined in the way that this is fxi xj at the point, say, xi and xj, and we will have p minus 2 fold integral here over the entire range of those variables. These integrals are except the two variables xi and xj. Leaving out these two variables, we'll have p minus 2 variables integrating over their range, and then looking at this as the joint probability density function of x1, x2, xp. What we'll be getting here, this coefficient I equal to 1 to p, then I is not equal to, it's better to have a different notation here, say L equal to 1 to p with L not equal to I. This is L equal to 1 to p, then L not equal to I, it's not equal to j d xi. So we will have this particular quantity to give us the joint probability density function of xi and xj, two random variables taken from this set. Similarly, what we can look at is this. So this would be the probability density function, not the joint, the probability density function of a particular random variable xi taken from this particular set. So we can also have a conditional distribution, conditional density function of, say, xi given xj and xk, say xi and xk, that would be given by the following, that this is xi given xj and xk. So this would be given by the joint probability density function of xi, xj, xk, this divided by the joint probability density function of the conditioning variables, that is xj and xk. Right. This random vector x that we had defined, comprising of these p elements x1, x2, xp, is said to be a set of independent random variables, is the set of independent random variables. Independence defined by statistical independence is a set of independent random variables if we have the joint probability mass function or the joint probability density function given as a product of the respective marginal probability mass function or the joint probability mass density functions. Say for example, in the case of discrete distributions, what we will be having for independent random variables is the following, that the joint probability mass function of x1, x2, xp would be given by the product of the respective probability mass functions given as the following. So this is for the discrete distribution. For discrete distribution, and if we have continuous distribution, then the joint probability density function of x1, x2, xp would be given by the product of the marginal probability density functions. This would be for the continuous random variable. Now let us now move on to some concepts which are going to be important for this particular course. So we define the expectation vector of this random vector x to be the following, that let us denote that by the vector mu, which is also a p-dimensional vector, which is expectation of this random vector. So that's defined as the following. So it's component wise expectation of the corresponding random variables x1, x2 and xp. Now these expectations, expectation xi in appearing in this particular vector, they basically are computed from the probability density function of the respective random variable xi that is coming in this particular direction here. Now given the information that x, the random vector, which is a p-dimensional random vector with an expectation vector as mu, if we make a transformation, say suppose we make a transformation which is say p-dimensional random vector to a random vector y, which is given by say ax plus b. Now here this A matrix, which maybe is a q by 1, which is a matrix of constants. So there is a matrix of constants, and b, so this now becomes q by p, and this is p by 1. So this particular component out here is q by 1. So b is say a q by 1 vector. So this is a vector of constants. So we take here this A matrix and this B vector out here to be non-stochastic elements actually, and then if we are now interested to find out what is the expectation vector of this newly defined random vector which is y, say let us denote that by mu y. So this would be given by A matrix, which is a matrix of constants, and that would then be given by expectation of x plus this B vector, right. So this would be given by A mu plus this B, right. Having defined this expectation vector, we move on to defining what we mean by the covariance matrix of this random vector x. Let us define the covariance matrix of this random vector x. Now let us denote that by sigma, which is the covariance matrix of x, which is given by expectation of x minus expectation of x, which we have already denoted by this mu vector, that into x minus mu transpose. So this mu is basically expectation vector of the random vector which is x, right. Now the ijth element in this covariance matrix of x, ijth element of this x is given by say sigma ij, which is simply the covariance between these two random variables xi and xj. So let us denote by mu I to be expectation of the ith component of the mu vector. Then this is xj minus mu j, where we have mu I is expectation of xi, and similarly mu j is expectation of the xj component, right. Now this is the ijth element of this sigma matrix. The diagonal elements basically are giving us the variances of the respective components, which are p in number. So this is just the variance of the ith component, which is expectation of xi minus mu I whole square, right. Now having defined this covariance matrix of this random vector x, we can define what is referred to as the correlation matrix. Correlation matrix of x similarly can be defined, say this is a row matrix which is holding the correlation components between the elements of this random vector. So it's a correlation matrix of this. Let us define that to be a matrix V half inverse times the sigma matrix into V half minus half. Let me also define what we mean by this V matrix. So this V matrix is a diagonal matrix holding the elements sigma 1 1, sigma 2 2 and sigma pp. So the V matrix is basically the matrix which is having the diagonal entries only and comprising of the variances of the respective components. Now we had seen what happens to when we have a random vector x and then we make a transformation from the random vector x to the random vector y, which was from p dimension to a q dimension lower or higher dimension. What we can also look at is given the information that x is a p dimensional random vector with expectation of x as a mu vector and the covariance matrix of x to be given by the sigma matrix. If we now make a similar transformation as to what we had done earlier to a random vector y, which is ax plus b, a and b are defined similarly as to what we had defined previously in this slide. So this basically is defined exactly in the same way that so this is that A matrix. So this A matrix is the matrix of constants, B is the vector of constants. So given that information, we are now trying to look at what is the covariance matrix of the new random vector that we have introduced, which is y. Now by definition that the covariance matrix of y would be given by, let us denote that by sigma y, for example. So this sigma y is expectation of y minus expectation of y into the transpose of this particular quantity. So we have already computed what is expectation of y from this random vector a. So this, we just replace this by the component in terms of x. So this would be expectation of ax plus b, this minus. Now expectation of y, as we had seen earlier, is a times the mu vector, this plus this b vector. So we have this quantity here given by this b, and then the transpose of this particular quantity comes out here. So what we'll be having is this b component cancelling out. So we'll have expectation of a x minus mu, that multiplied by the transpose of this quantity. So it's a x minus mu. So this would now be given by expectation of a into x minus mu transpose, and then we'll have this a transpose. So what we can see here is that this basically is a stochastic component here, and this A matrix and the A transpose matrix basically are the two matrices of constants, and hence we can take the expectation operator inside, and what we will be having here is A x minus mu to x minus mu transpose A transpose, and then this expectation of x minus mu into x minus mu transpose is nothing but the covariance matrix of x, which is given earlier by sigma matrix. So this is what we'll be having as the covariance matrix of the newly defined random vector, which is y. Now suppose we have two random vectors x and y, two different dimensions. We can also define what is the covariance matrix between the two components here. So suppose we have this a p dimensional random vector. So suppose we have this as p dimensional random vector, and we have y another q dimensional random vector. We can define what is the covariance matrix between the elements of x and the elements of y, similar to what we had defined by covariance of the components in that particular vector. This would be given now by expectation of x minus expectation of x vector, this multiplied by y. into expectation of this y vector whole transpose. So this is how one defines the covariance matrix between two different sets of random vector. It's important actually to look at the following, which we look at the partitions of the covariance matrix, what the partitions and what the elements actually can, what sort of interpretation actually can the elements of those partitioned elements can be having. Actually, partition of covariance matrix. So suppose we have this random vector x with the covariance matrix of x as sigma matrix. Let us make the following partition. Suppose this x vector, which was p dimensional vector, now is partitioned into the two following subvectors, say x1 and x2. Say suppose this is r by 1 and this is p minus r by 1. Similar to this x vectors partition, we can look at the corresponding partition in the mu vector, which is the expectation vector. So we can write the similar partition as mu1 vector, which is r by 1 vector out here, and then we will have the second subvector as p minus r dimensional. So this quantity here is expectation of the corresponding subvector what we had as x1 written out there. So this would be expectation of x1, and similarly this would just be expectation of this particular component x2 from here. Now if we look at the covariance, the partition that we have corresponding to the partitioning of the x vector, that's what we had written. So this by definition of the covariance matrix is given by the following, that it is this particular quantity. Then we look at what happens to this particular element when we look at this as the subvectors. So this would be x1 minus mu1. So this vector would be the second component, x2 minus mu2, and then the transpose of this comes out here, right? Now if one multiply the two and then take the expectation inside, or prior to that one can just look at what would be this particular matrix. This would be given by this x1 minus mu1, x1 minus mu1 transpose, and then this block here. So this would be comprising of 4 blocks. This would be the second component, x2 minus mu2, then this is x2 minus mu2 transpose, and then this element would be x1 minus mu1 into x2 minus mu2 transpose, and this would just be the transpose of this particular element there. So this element, once we take the expectation operator inside, would be, this would be a p by p matrix, which we denote by sigma 1 1, say. This would be a p by q matrix, which we denote by sigma 1 2, and then the expectation of the quantity which is here would be a q by p, which is denoted by, say, sigma 2 1, and this element, the last block here, will have this partitioning actually carried forward. So when we take the expectation of this block here, that's denoted by sigma 1 1. When we take expectation of this particular block here, that's going to be denoted by sigma 2 2 block, which is a q by q dimensional matrix there. And when we take the expectation of this block here, it's basically denoted by sigma 1 2. Now this sigma 1 1 element, if you look at carefully, this sigma 1 1 block here is expectation of this particular matrix here. And what's that? That's basically is the covariance matrix of the subvector what we had denoted by x1. Similarly, if we are looking at sigma 2 2, sigma 2 2 is nothing but the covariance matrix of the second block actually, that this particular x2 block of elements, and this sigma 1 2 matrix, which is the off diagonal block in this sigma matrix. So this is the covariance matrix of the two subvectors x1 and x2. That's what we had defined. So this is a covariance matrix of the two blocks x1 and x2, right? And this is just the transpose of this particular matrix, and that one can say that it is the covariance matrix of x2 and x1. So it's just differing by that particular transpose. Now we make a small note here that we had this sigma matrix in the partition form written as sigma 1 2, sigma 1 1, sigma 1 2, sigma 2 1, sigma 2 2. Now if we have x1 and x2 independent set of random variables, then what we'll be having is this sigma 1 2 will be given by a null matrix. Now if the elements of x1 are independently distributed of the elements of the x2 subvector, then we will be having this off diagonal block here sigma 1 2 to be given by a null matrix. However, the converse of this particular result is not true. But what I mean by saying that is that if we have sigma 1 2 to be given by a null matrix, then it does not imply that the elements of x1 and x2 are independent. It does not imply. It would only be implied if we have some other condition like what we had for bivariate distribution, that if we have the joint distribution of x1 and x2 to be given by a multivariate normal, then only we will have sigma 1 2 to be given by a null matrix. That would imply in such a situation that the elements of x1 and x2 are independent, right? Now let us move on to one characterization of the covariance matrix, what we are defining. So let us now look at one characterization, how we can characterize a covariance matrix. So characterization of a covariance matrix, we have the following result. Let me first state the result, that if we have any matrix which is positive semi-definite, it can be associated with covariance matrix of some random variable. So if we have a p by p symmetric matrix sigma, will be a covariance matrix if and only if it is positive semi-definite or non-negative definite. So let me write the result first, that any p by p symmetric matrix sigma is a covariance matrix if and only if it is non-negative definite. That is, alpha prime sigma alpha is greater than or equal to 0 for every alpha belonging to R P, right? So that gives us a characterization of a covariance matrix. So let us look at the proof of this particular simple fundamental result. So what it says is that if we have sigma to be the covariance matrix of some random vector x, then it's going to be positive semi-definite, non-negative definite. Other way around, if we have any matrix which is symmetric and it is non-negative definite, then we can associate some random vector to that particular matrix for which the random vector is going to have that matrix as its covariance matrix. So let us look at the proof of this result. Let us first look at the proof of the if part. Now suppose sigma is is a covariance matrix of some random variable x, covariance matrix of a random vector x. Then we take a alpha belonging to r to the power p. Then what we can say is that the following, that variance of alpha prime x. Now note that this alpha prime x is a scalar random variable, so it's the linear combination of the elements of that p-dimensional random vector. So by definition, this actually would be given by expectation of this random variable alpha prime x minus expectation of this alpha prime x whole square, right? Now we actually had proved a result that variance of, or rather the covariance matrix, we had proved the result, so that we can even use that particular result. We had proved the result that covariance matrix of ax plus b, this matrix is given by a covariance matrix of x, which is denoted by sigma a prime. So we can use this particular result in order to find what is the variance of x. Otherwise, from definition, one can also find out what is the variance, what is the expectation of this particular quantity. Let us look at that. So this is variance of alpha prime x. This is given by expectation of this alpha prime x minus alpha prime mu. Mu is the expectation vector of that covariant, that particular element, which is alpha prime x, this whole square. So this would be given by expectation. We take alpha prime out, so this is x minus mu whole square. So this would be given by expectation of alpha prime x minus mu. Then this is the transpose of that multiplied by this alpha vector. So this would just be given by alpha prime, then the covariance matrix of x, which is sigma alpha. So this is the variance of x. Now variance of alpha prime x is going to be given by this. Alpha is belonging to r to the power p. So since this is the variance of this random variable alpha prime x, which is going to be greater than or equal to 0. So we have proved that if sigma is actually the covariance matrix of any random vector x, then for every alpha belonging to r to the power p, alpha prime sigma alpha is going to be greater than or equal to 0, so that it is non-negative. It's going to be non-negative definite for every alpha belonging to r to the power p. So this basically implies that sigma matrix is non-negative definite. So let me just write that as NND. So that's non-negative definite. So the other way around, the only if part, we look at, suppose sigma is non-negative definite, we'll prove that sigma is a covariance matrix associated with some random vector x. Now since we have assumed that sigma is non-negative definite, say suppose it is non-negative definite of rank r, which is less than or equal to the dimension of this random of this matrix sigma. Since sigma is non-negative definite of rank r, we can write this sigma matrix in the following form, that it is C prime, where C is P by R of full column rank, right? Now since we have factorized sigma into this C prime form, let us now define a random vector y. Let y be a random vector of independent random variables, with say expectation of y given by a null vector. Now since we assume that the components y1, y2, yr, what we have for the random vector y, they are independent, then the covariance matrix actually would be given by a diagonal matrix using the result that we had stated earlier, that if we have the components of x1, that subvector, to be independent of the components of the x2 subvector, then the blocks which is holding the covariances of the components of x1 and x2 are going to be 0. So this would imply that the covariance matrix is diagonal without loss of generality. We take that to be an identity matrix. So the covariance matrix of Y is given by, say, this identity matrix of dimension R, right? Now Y is that set of independent random variables with expectation of Y vector to be a null vector, and the covariance matrix of this Y vector to be an identity matrix of dimension R. Now let us make a transformation from Y to X, where X is given by C times this Y. Now the matrix C, what we had defined earlier, which is a P by R matrix, which is a matrix of constants of full column rank, so that's of rank R. So with that C matrix, if we now look at what is this X matrix characteristics as far as its expectation vector and its covariance matrix are concerned, we will have, this implies that expectation of this X vector would be given by a null vector, because this is equal to C times expectation of this Y vector, and expectation of Y vector being a null vector, this would imply that it's just a null vector. And then the covariance matrix of this X vector is covariance matrix of this C times Y vector, and that would be given by C times covariance matrix of Y into this C transpose matrix. Covariance matrix of Y, what we have assumed, is an identity matrix, so it's a covariance matrix associated with IID random variables, actually, with variance equal to 1. So this would be given by C times this IR matrix, C transpose, so this is equal to C prime, and which is nothing but that sigma matrix. So this would imply that this sigma matrix, what we had just taken as a non-negative definite matrix, it's now the covariance matrix of this random vector X, right? So this would actually prove that sigma is a covariance matrix. So we have proved the result that any P by P symmetric matrix which is non-negative definite is, if a P by P symmetric matrix is non-negative definite, is a covariance matrix if and only if it is non-negative definite. We just put it as a note, the following result, that if covariance matrix of X is not positive definite, then with probability 1 the elements of X are linearly related. With probability 1 the elements of X are linearly related. What do we mean by this is the following, that suppose sigma, the covariance matrix of this X random vector, is not positive definite, then there exists an alpha belonging to R to the power P such that we will have alpha prime. Now this alpha vector belonging to R to the power P, of course alpha is not equal to 0, so this goes without saying that this alpha is not equal to 0, then this alpha prime sigma alpha, that is equal to 0. So there exists some alpha such that this alpha prime sigma alpha is equal to 0. Now what does this mean? This means basically that what we had seen earlier is that this alpha prime sigma alpha is nothing but variance of this alpha prime X. So we have this variance of alpha prime x given by alpha prime sigma alpha. This is equal to 0 for some alpha which is not equal to a null vector. What it means is the following, that probability that alpha prime x is equal to its expectation alpha prime mu, this is equal to 1 for some alpha which is not equal to 0, right? That is, what we have is alpha prime x minus mu, this is equal to 0, this probability is 1 for some alpha which is not equal to 0, right? So this basically would imply from the statement that we have made here that probability that this particular linear combination is equal to 0, this is equal to 1 for alpha not equal to 0. So this would imply that probability that summation alpha I, the ith component, xi minus mu I, this is equal to 0, is equal to 1 for some alpha which is not equal to a null vector. So this would imply that the elements of x minus mu, that is these xi minus mu i's, are linearly related with probability 1, right? So we will have the elements of the xi components, because these mu I components, they are basically constant components. So we will have the elements xi's actually being linearly related if we have the matrix sigma, the covariance matrix, to be a matrix such that it is not positive definite, right? Before we move on to random sampling of from a multivariate distribution, we look at two concepts, which is moment generating function, from where we can get actually joint moments of the components which are there in that multidimensional random vector. So let us look at that. Moment generating function. So the concept of this moment generating function of the random vector x is basically trying to generalize what we actually have for univariate random variables. So we have, say, this x, a p-dimensional random vector with expectation of x given by this mu vector, covariance matrix of x being given by the sigma matrix, then the moment generating function mgf of this random vector x is defined to be the following, that it is expectation of e to the power t prime x, right? So this is how one defines the moment generating function of the random vector, the p-dimensional random vector x. Now given the information, now this provided the expectation exists, now the moment generating function of this random vector x actually would also lead us to the marginal moment generating function of the components of x in the following way. Now if you look at how to get the marginal moment generating functions, say we are looking at this, the moment generating function x1, x2, xn at these points x1, x2, xn, that's what is our mxt, the moment generating function. So from here, if we want to find the marginal mgf of xi, so that would be derived from this, which is the joint moment generating function of the components of x in the following way, that the marginal moment generating function of xi at the point ti, that would be given from the joint moment generating function of x1, x2, xn with 0 at all other points except the ith position, which is say ti. So this is the ith point. So this is what is going to give us the marginal moment generating function of the component, which is xi. To see how that is true, it is trivial to look at the expression of this particular joint moment generating function of the random vector x. So here, if we take all the ti's except one ti component here as 0, then this particular term here, which is this term, is a summation ti xi. So here, if all the ti's except one particular ti is 0, then this sum is nothing but just ti xi. So expectation of e to the power ti xi is just the moment generating function of this particular component, which is xi. Now given this particular moment generating function, one can actually look at the joint moments actually of any order, provided the corresponding moments exist, can be obtained from the following. Say suppose we are looking at this particular joint moment. We can obtain this joint moment for this set of random variables x1, x2, xp, or any set of random variables derived from it, using the moment generating function in the following way, that it is the partial derivative of the joint moment generating function, the derivative with respect to all these ti's, this evaluated at t1 equal to t2 equal to tp, this equal to 0. So this is how, from the joint moment generating function mxt, one can get to the joint moments of any order, provided that order moment exists. One can get to the joint moment derived from that, right? Now, a result which is particularly useful in some applications, as we move in this particular multivariate normal course, we will see that we are very frequently concerned with a quadratic form of the following nature, that suppose we have this x, this multivariate vector with expectation of x to be this mu vector, and the covariance matrix of x to be this sigma matrix. Then if we define the quadratic form as x prime ax, this is a quadratic form in x, so where this A has, of course, the interpretation that it is a matrix of constants, so it's a non-stochastic matrix. So this is, say, a p by p matrix of constants. Then expectation of x prime ax is the expectation of this particular quadratic form. So this actually can be obtained in the following way, that now note that this is a scalar quantity. This we can write as expectation of the trace of this x transpose ax. We can use the result that trace of ab equal to trace of ba. So what we can write is the following, that this is trace of a x transpose. We can now take the expectation operator inside the trace. So this would be the trace of a expectation of x transpose. Now let me give this equation number 1. Now in order to find out what is expectation of x transpose, we see that this sigma is expectation of x minus mu into x minus mu transpose. If you look at what the expectation of this quantity is, so it would turn out that this is expectation of x transpose minus mu transpose. Just open it up and then take expectation inside. So this would tell us that expectation of this x transpose is nothing but sigma plus mu transpose. So if we use this equation number 2 in equation 1, so using this equation number 2 in 1, what we get is the following, that what we had there was trace of this particular quantity. So we have expectation of x transpose Ax that was given by trace of A expectation of x transpose. Now we have obtained that in the form of this 2 here, that expectation of x transpose is sigma plus mu transpose. So this would now be given by sigma plus mu transpose. So this expression now would just be given by trace of A sigma, this plus trace of A mu transpose, and then that can be written actually as the following, which is mu transpose A mu, using once again the result that trace of AB equal to trace of BA. So what we have is the following result, that if we have that multidimensional random vector X with a mean vector equal to mu and a covariance matrix equal to sigma, then expectation of this quadratic form is just given by this trace of A sigma plus mu transpose A mu. Similar result for the variance of this quadratic form can also be derived.